In this video, we solve problem 4.7.11 from Nagle's Fundamentals of Differential Equations with Boundary Value Problems, 7th edition. We're asked to find a general solution to the given Cauchy Euler differential equation for t greater than or equal, or strictly greater than, 0. Notice that the power of t and the order of the derivative multiplying it are the same. There's a t to the first there, and that's a first derivative implied. That's a second derivative and a t squared. There's no t's here, and that's the 0th derivative for the original function. That's what makes it Cauchy Euler. And since we're dealing with a homogeneous Cauchy Euler equation, we start by letting y equal t to the m. Since it's second order, or actually we're going to let z equal t to the m because z is our dependent variable here. Since it's second order, our general solution will be C1 Z1 plus C2 Z2, where Z1 and Z2 have this form or a form related to that, depending on the roots of a certain polynomial equation. So we're assuming this is a solution, and we'll take the first and second derivative. I'll use prime notation rather than Leibniz notation. We know that these are derivatives with respect to t, and we're assuming that this is a solution to the equation. So if I take the first and second derivative and I substitute all of this in, the expression should be satisfied because we're assuming it's a solution. Okay, so let's let z equal t to the m. Then z prime is m times t to the m minus 1. Z double prime is m times m minus 1 times t to the m minus 2. Distribute that m if you want to. And then substitute into the differential equation. So we have t squared times m squared minus m times t to the m minus 2. Plus 5t times dz dt, which is z prime, or m times t to the m minus 1. Plus 4 times z, which is t to the m. If this is a solution to the equation, then that must be equal to 0. Now, whenever you're multiplying powers of t, you just add the exponents. T squared times t to the m minus 2 is going to be m minus 2 plus 2, so it's going to be t to the m. And I've got a t to the first and a t to the m minus 1. M minus 1 plus 1 is another t to the m, and there's a t to the m over there. So you can factor out t to the m from everything, and then you're left with this. M squared minus m plus a 5m from that term, and then a 4 over there, equals 0. And we want this to be 0 for all values of t. When this times this equals 0, we can say either this is 0 or this is 0. But we're told at the beginning that t has to be strictly greater than 0. So that means this is non-zero. If t is positive, this is never 0, so our polynomial must be 0. And that is the characteristic polynomial for this Cauchy Euler equation. If you can find the values of m that satisfy this, then those values of m will lead us to find the linearly independent solutions of the differential equation. Well, that's actually really easy to find, this factors this way. I need two numbers that multiply to give me 4 that add to 4. Positive 2 and positive 2 work. So we actually have a repeated root. That equals 0 when m plus 2 equals 0. So that means that m1 and m2 are both equal to what we get when we solve that for m. So that's just going to be a negative 2. We happen to have a repeated root this time. Now careful here. We are dealing with a Cauchy Euler equation. So y1 is not e to the m1x or e to the m1t. y1 is t to the m1. This is t to the negative 2. And our second linearly independent solution, whenever we have a repeated root for Cauchy Euler, comes from not multiplying by an extra t, but multiplying by a log of t, natural log of t. So we'll have t to the negative 2 times natural log of t. So those are our two linearly independent solutions, and the general solution just comes from taking those guys, multiplying them by constants, and then adding them together, and you'll be good to go. Y is equal to C1 Y1 plus, oh, I keep calling them Y's, these are Z's, sorry. The dependent variable they gave us was a Z. So Z is equal to C1 Z1 plus C2 Z2. So Z is a function of t, and it's equal to C1 times t to the negative 2 plus C2 times t to the negative 2 natural log of t. And this will work on the interval from 0 to infinity. So I guess I need to call that Z1 and Z2. That's a Z, and that's a Z, and that's a Z. Always good to state an interval of existence as well.